From this video onward, we are going to start our discussion on thread pools. So far, in almost all our parallel implementations, we had to make sure that the spawn thread are managed and talks are divided among them properly. But if we had any mechanism which will handle these overheads for us, that would be great. Ideally, we would simply pass the tasks to an API and simply tell that API to parallelize the execution for us. With thread pools, we will be able to have that luxury. In this section, we will start our thread pool implementation in very basic level, and we will gradually grow it to one which can handle complex operations like waiting and work stealing. In most systems, it is impractical to have separate threads for every task that can potentially be done in parallel to other tasks, but you would still like to take advantage of the available concurrency where possible. A thread pool allows you to accomplish this. Tasks that can be executed concurrently are submitted to a pool, which puts them on the queue of pending work. Each task is then taken from the queue by one of the worker threads, which execute tasks before looping back to take another task from the queue. So basically, thread pool is going to have work queue or task queue to store all the tasks put into the thread pool and set of threads which will run iteratively by popping one task at a time from each thread. When we have tasks to be done, we can simply submit that task to the thread pool. If the external entity has to wait until submitted tasks get finished, in such cases, we should have the ability to access the future associated with that task, so that external code can wait on that. So these are the basic functionalities that any thread pool should offer. Okay. Let's start our implementation of thread pool from simplest of thread pools possible. The thread pool we are going to discuss here is going to have fixed number of threads that process work. When you have work to do, you call a function to put it on the queue of pending work. Each worker thread takes work from the queue, runs the specified task, and then goes back to the queue for more work. Okay. Let's see how to implement this type of simple thread pool. Okay, here we need a few things first. We need a flag variable to stop the execution of all the threads. For that, I'm going to have atomic Boolean type variable called done. Each thread will iterate until this flag is set. If it is set, then all threads have to stop the work, and this means we are not going to use this thread pool anymore. Then, we need thread-safe queue here to store the tasks put in to execute. Each thread is going to check this queue for next task after it completes the current task. You can use any of the thread-safe queue implementation we have done so far for this, and we are going to store tasks or callable objects on this queue. So let's set its type to std function so that any thread can be passed as the task. Then, we need a vector to store the threads in the thread pool. And then, we need a joiner object to guarantee the joining of each thread of the threads in the thread pool. Then, we have to define functionality of each thread. Each thread is going to perform very basic set of functions. Each thread will iterate until the done flag is set. So, we can have a while loop which checks the done flag in each iteration. Then, it will try to pop a task from the working queue. So let's have a variable to store the popped task, and then we can use try_pop function in our thread-safe queue in this way. If try_pop function returns true, which means we have successfully popped tasks from our pending queue, then we can simply execute the tasks. Otherwise, we can yield this thread to give other threads the CPU space. This function is going to execute by each of the threads in our thread pool. Okay, now all we have to do is to construct this thread pool with few threads. So first, let's initialize our done flag to false. And also, we can initialize our joiner object with the threads vector. The amount of threads we are going to have here is equal to the value returned from the hardware concurrency function. So let's query that value as well. Then, we can store the number of threads in our threads vector, and each of these threads are going to run the function we defined before. If any exception happens while launching a thread, we have to catch it here. So let's have a try-catch block wrapping the construction of these threads. And if we catch an exception, we can simply set the done flag to true, which will indicate existing threads to stop their execution. Also, in the thread pool's destructor, we can set done flag to true as well. Now we need a way to push tasks to the thread pool. For that, we are going to have another function called submit. This function will simply push the tasks to the working queue. That's all. Okay, now we have the most basic thread pool in our hand. We can submit tasks we want to perform via submit function, and rest will be taken care by the thread pool. Now let me show you simple usage of this thread pool. Here, I'm going to create 100 lambda expressions iteratively and pass it to the thread pool. In that lambda expression, we are going to print out the iteration counter and the thread ID. So here, let's construct our thread pool first. Then, in a for loop, I'm going to submit the lambda expressions to our thread pool. Note, in our submit function, we allowed any type of functions or callable object to be the argument, so we can use lambda expressions here as the tasks. I have to specify the default capture in the capture list so that we can access the I variable inside the lambda expression. Then, we have to print out the value of the I variable and the thread's ID, which is going to execute this task. Okay, let's run this example and see what the outcomes are. Okay, as you can see, there are 100 lines in our output, which means all the tasks have been executed properly. Also notice the thread IDs in each print statement. You can see in this output, same thread have produced multiple lines in the output. So this output guarantees that the validity of our thread pool implementation, which means same thread have executed multiple tasks. Now this is how it should be, as I have only 8 cores in my CPU. So hardware concurrency function will return 8. So in my thread pool, it will only have 8 threads. But still, we have pushed, or we have passed, 100 tasks to that. So one thread should have to execute more than 1 tasks. In this case, around 12 tasks. So this output guarantees the validity of our thread pool implementation. Even though this implementation has sufficient enough functionality to be used in some applications, still, it lacks some of the important properties. For example, calling thread do not have the ability to wait on the tasks that it passed to the thread pool, as we do not have return any object like future back to the caller from the submit function. Also, the threads in our thread pool do not have the ability to execute tasks while they are waiting on another task to finish. So our current implementation does not contain these basic functionalities. So let's see how to improve our implementation to have these basic functionalities.